just say a word that I have been also in Huazhong University, and I have taught courses 2 times. I think it was in 2015 and 17. I think. Okay.
Okay. That's great. So can you see my slide? Is the recording working properly?
Yes.
Okay, great.
Yes.
Yeah. So both of you, I think it would be great if you can come back to Wuhan and visit Huazhong University and during summer or for an invited talk or other opportunity like that. I think it would be great helpful. We have a lot of people working on images and also applied math and application to images and related stuff. So yeah, I think that
for sure in the next travel in September or October. No, for sure.
Great. If you have time, and you can just contact Lee and we can exchange so that you can you have a paid and invited travel to Wuhan. I think it'd be great.
For sure. Thank you.
Okay. So yeah, I guess I can start.
Yes.
So thanks all for the kind invitation and so my name is Zhenyu Liao, and I'm now working at the School of Electronic Information and Communication in Huazhong University of Science and Technology in Wuhan. And so I changed a little bit the title of my talk today. So starting with random matrix for machine learning, but with applications ranging from compression and training of neural nets. So here will be the outline today. So we'll start with an introduction, talk about the motivation, why we care about the so-called random matrix stuff, and why it's important to apply these mathematical tools in machine learning. And then I'll try to cover 3 recent results on the application of random matrix theory in machine learning. So starting from basically compression of shallow, for example, single hidden layer neural nets to deep neural nets. And then at the very end, I will try to mention a little bit, if I have some time, so how to apply random matrix theory to characterize the training behavior, the learning dynamic of neural nets with gradient descent. Great, so let's start with the introduction. So the motivation is that in fact we are, so everybody mentioned this keyword today, we're in a big data age today. So for me, big data basically means that we have a lot of data, and the data are of complex nature, of high dimensional. So in the notation here, so we have data points, we have data vectors xi to xn, and each data vector is of dimension p. So small n and p in my notion of the big data, they're all large. Okay, and to handle those kind of high dimensional and big data, we're in need of a large scale machine learning system. So here the size of the machine learning system, this capital N, is also large. So for me, it's big data age today. We're working in the region where small n, small p, and large n, they are all large. Okay, and consider things in this region is natural because for many people playing with computer visions, images, and videos, for example. So this ImageNet data sets is one of the most popular computer vision data set, and it's in average contain images of dimension equal to about 0.2 million pixels, and in total there are about 14 million images of such high resolution images. In general, we have this MP, small np, both large, and in considering this region, it's important because in this region there are many counterintuitive phenomena. For example, something I will mention in a few slides, the curse of dimensionality in this so-called high dimensional region. Okay, so basically things are different than our small dimensional intuition that we can see and observe every day. And we need new mathematical tools to have a complete understanding of this, what's happening in this new regime, and characterize how things are working, how existing algorithms are working in this new and high-dimensional regime, and eventually to propose new and in fact fix some existing methods that are not working properly and making things perform well in this large dimensional regime where small n, small p, and capital N are all large. And random matrix theory and high dimensional probability provides us the tool to do this. And I will try to convince you with a few examples. So here is the toy example I try to play with and show why things we consider to be counterintuitive. Okay, so here we focus on the idea of Euclidean distance, and we consider a very simple example of doing Gaussian mixture classification. So we have data points that are in dimension P, okay? So P is large, we're considering the high dimensional regime, and the data points are drawn from a binary, so two-class Gaussian mixture, so either from class C1 or from class C2, with different, so they are just multivariate Gaussian with possibly different means and covariance, okay? Mu1 versus mu2, and C1 versus C2. And after a pretty simple, straightforward calculus, we can use Neiman-Pearson test to verify that the classification about data point drawn from the above binary Gaussian mixture is only possible if these two Gaussian spheres are sufficiently separate from each other. So this is pretty intuitive to understand. And they have their mean, so mu1 minus mu2 should be the norm of this difference in means should be larger than some constant, and the covariance operator norm of this covariance should be larger than some constant, but divided by square root of p. So only both of this holds. It is only at least one of this condition holds. It is possible to classify the above Gaussian mixture for some constants that are independent of the dimension. Okay. Now, what can be interesting is we will take the two inequalities to be equal. So basically, we take this mu1 minus mu2, the norm to be some constant, and the operation norm between C1 and C2 to be some constant divided by square of p. Okay, we just take equal sign. And we call this so-called non-trivial setting. And it's non-trivial because the classification is still possible because we just take the equal sign, but it's not easy, right? In the sense that we are not letting their difference to be very large. So the Gaussian are super close, super far away from each other, in which case the classification becomes trivial and we can only compare basically the norm of our data vectors to distinguish whether they belongs to C1 or to C2. Okay, so in the region we take equal sign in this box equation. That's the hard but doable setting for this Gaussian mixture classification. Okay, and in this setting, after a few calculus, we can derive the second box equation, and that is very interesting and counterintuitive. Okay, so basically this equation tells us for P large, okay, for NP large, N is the number of data samples, and P is a dimension of our data, okay, dimension of a data vector. For NP both large, then the normalized Euclidean distance between any two data vectors, okay? So any xi from a different xj, so this distance evaluated to the power of 2 is approximately equal to a constant, okay? And we know precisely the expression of this constant is basically a averaged of the covariance matrix, the trace of this average covariance matrix after some normalization, okay? But this equation holds regardless of the classes of the data vectors, okay? So this means for NP large in the higher dimensional region, what we have is you take any two data vectors, okay? Xi and Xj, they may belong to the same or different classes. But as long as you compute this normalized Euclidean distance, you'll always get the same constant. And this constant does not tell you, unfortunately, whether they are from the same or different classes. So in this sense, basically the idea of Euclidean distance no longer really actually makes sense and cannot tell you, at least in the setting where NP are both large, where we're in the high dimensional region, whether the data points belong to the same or different classes, whether they are close to each other or far away from each other. And we have other intuitions, but I will not try to mention those. And here is a figure and the phenomena I just described. Okay, so our left-hand side is a small dimensional region. Okay, for everything small in two-dimensional or even three-dimensional world we're living in, we have the idea of distance and being close or far from each other. Okay, so here we have these red crosses from class Z1, for example, and the red circles from class C1 and the blue crosses from class A2. And we see that they belong to different class because each data point from the same class are closer in distance from each other. And if we take a single data point, a single blue cross and the red circle, they are far away from each other. So we had this idea of Euclidean distance and being close or far away from each other. However, as we have done in the calculus here in high dimensional, so in our right-hand side, we have a totally different mental image, okay? So in the high dimensional region, in fact, the geometry are super different. And if we consider data point living in the p-dimensional Euclidean space, in fact, basically almost all the volumes in the space are very shrinkage into a very thin shell, and within this very thin shell, all the data points are there. So basically, if we measure the distance between any two data points, so whether they are blue crosses or whether they are red circles, we always get the same distance. So they are approximately at the same distance from each other, okay? And this is exactly we have calculated here. This distance is exactly given by this constant tau. So we have a very different image, and it seems that things are mixing up in high dimensional, and we do not expect to make the standard distance-based machine learning classification approach works. Okay. However, we still have some ways to make things working, and that's for totally different reasons when we are dealing with small dimensional versus higher dimensional image. Okay, so here we observe that in the higher dimensional region where NP are both large, first that if we observe only two data points, okay, any two data points, Xi from any class CA and Xj from CB, then using only the Euclidean distance is impossible to tell us whether they are from the same or different classes. Okay, we always get approximately the same constant tau, which is independent of their classes of the data points. Okay, so these two data points are not pairwise classifiable. However, if we do something, if we collect a lot of data, so if we have n data points, so x1 to xn, and we try to collect all the information in a matrix, okay, in this so-called Euclidean distance matrix, which basically collect all the Euclidean distance of two data points in its entries, okay? And we do something different, okay? We are not trying to focus on the entry of this Euclidean distance matrix, which is not going to be very informative because data pairs, data vectors are not pairwise classifiable. Okay, we always get a constant tau. However, we try to collect the spectral information, we compute its eigenvector and eigenvalues. And in doing that, since there is a collective behavior of all the data points that's drawn from the similar distribution, this in fact allows us to perform classification. And I'll try to do a few simulations to numerically support these two dual observations. Okay, so again, here is the distance. Okay, here is our left hand side is the small dimensional region with p equal to 5, and here is a histogram of the distance between data from the same or different classes. Okay, for p equal to 5, we have our small dimensional intuition still holds, and we say that data points from the different classes are larger. Okay, they are far away from each other, giving this red histogram. Okay, and we also have the blue one, which are essentially draw from computing from the Euclidean distance from data from the same classes. Okay, we have this idea of being close to or far away from each other. However, if we move to our right hand side, okay, p equal to 250, not super large number, we see that this red and blue histogram overlap. That's given also by our previous calculus. We know that in fact for high dimensional regions, the distance is approximately always the same constant, independent of whether the data points are from the same or different classes. So this is to support our first item. Okay, and then we compute the Euclidean matrix. Okay, we try to do this for a lot of data points, and we collect all this information, all this Euclidean distance in a matrix. Again, our left-hand side is p equal to 5, and we get looking like a block, a 2x2 block matrix. Okay, and this is I try to do this on purpose because I separate all the n data points into two parts. So first, from the first data points to the n over 2. So all the the first half of the data points are drawn from class 1, from C1, and the remaining half are from C2. Okay, so this in the case of p equal to 5, so small dimensional intuition holds, leads to this Euclidean distance matrix. And we understand it because this first block, okay, we say it's a bit darker. It's a bit darker because we are trying to compare things. Already arranged the first half, all the data, all the first half data from the same class, they are closer in distance to each other. So this leads to, in this first diagonal block of the matrix, that we're comparing data points from the same class, from class C1, and they're closer to each other, so they have a smaller distance. Okay, and this explains why the color is darker, okay, with a smaller value of pixels. And this holds for the second diagonal block as well. Okay, we say all the both the two diagonal blocks are darker because for p equal to 5, we have our small dimensional intuition holes, and data points from the same class are closer to each other with a small Euclidean distance, and therefore the values of the pixels of the matrix is darker, is smaller. Okay, and we also understand why this off diagonal, okay, this block and this off diagonal block are whiter. Okay, they are whiter because they are trying to compare data points from different classes, and their distance is larger, and they have a larger value, okay, of this in this Euclidean distance matrix. Okay, so that's why we understand why we have this block behavior, but only in the case of p equal to 5, okay, small dimensional region. If we go beyond that, okay, we move to the large dimensional region, we see P equal to 250, okay? We see everything's kind of gray, okay? And we understand this as well because we have to a calculus saying that in the large dimensional non-trivial region, in fact, the Euclidean distance matrix is approximately, all its entries is approximately the same constant. That's a constant I call tau, okay? So basically, it's a matrix filled with the value of tau, apart from its diagonal entries, because that's equal to 0, right? So it's almost always equal to tau. And since we do not have a block shape, we clearly observe, at least visually, that it's very different from the scenario where P equal to 5, okay? However, what is even more interesting is here we plot the vector of V2, so the second eigenvector that corresponds to the second largest eigenvalue of the matrix E, okay, of the Euclidean disk matrix. And we say, well, kind of magically that this two eigenvector behavior look very close to each other. So they look like the same. And what is more important is they tell us that the first half of the data is drawn from some class, for example, class C1, and the second half is from another class, okay? We see a plateau here in the eigenvector of both cases. So in the small dimensional and in the large dimensional region, okay? This is very surprising because we already see that the matrix themselves are very different from each other. But if we choose and the right thing to look at, okay, the eigenvectors associated to the second largest eigenvalue, then we still can do classification, okay, and telling us that the first half of the data are from the class and the second from another class, okay. But we must choose this V2, so not V1 or not V3, and for some reason. And we understand all this, so I will not giving details about this, but random matrix tools basically tells us why this is happening in the large dimensional region with this P equal to 250, okay? So with the tool of random matrix here, we can totally understand, at least in the high dimensional region, why things is working here. So even we observe a all gray matrix, we can still, but choosing very carefully for example, an eigenvector to retrieve information about the class of data points. Okay. Great. So after an introduction, I think we're pretty convinced that at least in the case of Gaussian mixture classification, things are very different when we focusing on the small or large dimensional region, but we have some kind of tools to understand how things are working, at least in the large dimensional region. Okay, so here I will try to mention a few recent results and how to use these ideas on neural network compression. And first, we're going to start with the simple case where we focus on the shallow neural network with only one hidden layer and random widths. Okay. So here is our system model. So we have some input data X. Okay, and they are data vectors of dimension P, and we have an output. And this data are linear transform with some first layer widths, okay, this W matrix having n neurons, okay, so the row number, the number of rows of this W matrix is capital N and corresponds to a neural network with n neurons, okay. And once we have this WX matrix, it's then passing to this hidden layer having n neurons with some nonlinear activation functions. Okay, so I did not sigma here. And then we get the feature after this first hidden layer of the neural network, which is given by this big sigma matrix, okay, equal to sigma nonlinear activation applied entry-wise on the matrix WX, okay. So we care about, in this simple setting, in fact, we care about what's the behavior of this correlation matrix or this gram matrix, sigma transpose sigma, okay, which basically tells us what is the type of correlation look like after the transformation of the neural network, okay? So when the data inputs, when transformed with the neural nets, what's their correlation look like? And whether this correlation behavior is a explicit or a complicated function of the nonlinear activation function or the weights, the distribution of the weights or not, okay? So for now we consider the case where the random weights are Gaussian, okay? So we have Gaussian random weights, and this is used in practice as initialization of to train before, so to train using gradient descent of neural nets, okay? We'll first try to consider this setting, and then we extend this to random and ID entries, okay? So with a few calculus, in fact, we can write this correlation matrix or this gram matrix as the sum of capital N rank 1 matrices. And there are papers in the literature already telling us that if the number of neurons is pretty large, okay, we have capital N goes to infinity, then the behavior of this correlation is characterized by a so-called expected kernel matrix, which basically because, in fact, this correlation matrix will converge to the expectation over the distribution of your random weights. Okay, so we get a kernel matrix Kx given in this form. So N is a small bi-M matrix because we have N data points, okay? And it's a function, of course, of the distribution of the random weights. Okay, so since here we are taking the expectation with respect to the random weight vector, and also, of course, a function of the nonlinear activation function sigma here. Okay, so our objective in the following is to understand the structure and behavior of this kernel matrix K. Okay, and what we're trying to do is to find how this kernel matrix K depends on the distribution of W and the nonlinear function. So if we understand this in a very explicit manner, then what we're trying to do is to use different weights or activation function, but without changing too much the underlying kernel K, okay? So basically, in doing that, we try to, for a given neural net, okay, we have a fixed kernel matrix K. Then we'll try to find another kernel matrix K that corresponds to a different neural net, but these two kernels are similar to each other, okay? And we hope to find a second neural net that is more computational, that can be computed much more easily. For example, with sparse weights and sparse and quantized activation functions. So have good numerical properties, okay? But without changing the underlying kernel so that their performance of this, the performance of these two neural nets are same, okay? And we're going to do some analysis and propose our method, okay? So the starting point is we assume the data to be Gaussian mixture, okay? So this allows us to do some mathematical analysis, and we'll see later that in fact we can extend these assumptions to more realistic assumption for the data. But now for simplicity, let us assume the data vectors are Gaussian, okay? Our Gaussian mixture, and we have K class of them. And then we consider again the large dimensional region where MP are both large, okay? So we are in the high dimensional region where we can apply our random matrix truths. Under these two settings, we have the following results, okay, which basically tells us the following, okay. So for the kernel matrix that I just described in my previous slide, so for this kernel matrix, then we know that this kernel matrix K is going to look like another kernel matrix K tilde, okay, in the sense that the operator norm of these two matrices are small. And this K tilde is simple, okay, simple in the sense that, of course, it's going to depend on the data X, on the activation function, but it depends on the activation function only in a very explicit and simple manner, only via the following three scalar parameters, okay? We see that for Z to be standard Gaussian, so standard Gaussian random variables, we can define this D0, D1, and D2. These are all basically expectations of the derivatives or not of the nonlinear activation functions, okay? So we know that this K tilde only depends on the nonlinear activation function only via the following three parameters. And more surprisingly, perhaps, it's independent of the distribution of the random weights as long as the random weights have their means are univariants. Okay, so here, so just take a step back. We try to think about this result. It basically tells us that, in fact, we care about that kernel. That kernel approximately look like another kernel matrix is K tilde, and it's very easy. It's very easy in the sense that it depends on the activation, but in a very simple way that we can explicitly characterize, and it's independent of the distribution. So as long as the distribution of random weights have zero mean and univariance and not independent entries. So we have a very large degree of freedom in the design of this K tilde, okay? Changing the sigma activation function or the distribution will not change the behavior of K tilde, and as a consequence of this result will not change the behavior of kernel matrix. And this allows us to do the compression, okay? So I list a few, proof sketch, but they are not very important. Essentially here we rely on the intuition of our high dimensional statistics, okay? If it is not on high dimensional, then we cannot do the proof. But as long as we are in the high dimensional, magically things simplifies and we can obtain our theorem. So I will try to skip this proof and directly dive into the use of this theoretical result to do neural network compression. Okay, so with this obtained result, in fact, we can basically choose an arbitrary weight function. Okay, weight matrices distribution W, because it's not going to change the behavior of a kernel a lot, and we also have pretty large degree of freedom of the activation function sigma without basically affecting a lot the behavior of the kernel matrix. So what we will try to do is we'll try to use sparse and binarized weights instead of the dense Gaussian weights, because in the literature people always prefer using uniform Gaussian weights because that's working in practice pretty well. Here we propose to use something, more computational feasible. Okay, it's the random weights can have some probability to be equal, or otherwise to be plus and minus some quantities. But these are well designed, so it's take only either 0 or plus minus 1 up to some scaling. So it's sparse and binarized. Okay. So this can be computed and stored much more efficiently than dense Gaussian. And also we can do the same thing for the activation function, okay? We can take the activation function to be sparse when quantized, but without changing the parameters D0, D1, D2 when compared to the original neural network that we would like to compare. Okay, so basically the algorithm will look like the following. You give a neural network. So for a given neural network, we just tweak the random weights according to the sparse and binarized weights. And then we compute the D0, D1, and D2 of this 3-parameter of the original network and design a different sparse and quantized activation function that's have the same parameters, okay? In doing that, we making the neural network much more computational, easy, and that can be stored and compute much more faster, but without changing a lot the behavior of kernel metrics, okay? And here is a figure that we try to perform numerical validation of our proposed methods, sorry. And the x-axis of this figure is the memory. So we for storage convenience, we hope to have the number of bits as small as possible. So we hope to have a small memory. And the y-axis is MSE, so for a regression problem. So we hope this MSE to be small as well, okay? And so the left bottom corner of this figure is always stands for good methods. And there we directly say our proposed scheme, okay? This is blue curve. And other curves in black or in red are, for example, very state-of-the-art methods in compression and quantizing simple layer neural network, okay? So this low pressure random free feature or natural methods, okay? So they always get, in general, not as good as performance as our proposed method or much larger memory, okay? And another comment I would like to make is, so even though our results are derived based on a Gaussian mixture modeling of the data, here we test our proposed methods on real world data, okay, on a so-called census data set on UCI REPL, okay? So even though the theory is derived, everything's precisely proved for Gaussian mixture data, and the proposed method seems to work pretty well on a realistic real world data, okay? As long as the dimensions are pretty high, okay, in hundreds, for example. So here I have covered the first part of the first stuff I would like to mention is how to apply random matrix and higher dimensional intuitions to compress single hidden neural network. And then I will try to extend this idea to deep neural networks, okay? Because people care about this, right? Everyone cares about more about deep neural nets, and in particular, when the neural network is not random weights, okay? They want to train the neural nets to get pretty good performance, okay? And what we're trying to do is try to first focus on the first bullet, okay? We focus on how to extend what we have done in the shallow case to deep neural nets. And here's the network we're trying to consider, okay? So it's a L layer neural net with very possibly different activations functions in each layer. So we first apply some linear transform W1, and then entry-wise nonlinear T sigma 1, and then W2, and then sigma 2, etc. So we have L layers, and the output is a scalar, okay? So that's the neural net we're going to evaluate. And for this different deep neural net, basically, and by the way, it's a fully connected, okay, a neural network model. For this specific model, we basically get the same conclusion, okay? So we still care about the output feature, okay, output feature of any after L hidden layer, for example, so denote this big sigma L. And of course, it depends on all the previous activation functions and random weights. So for the moment, we still let the weights to be the weight function, the weight matrices to be random, for example, having ID entries, okay? And then we focus on this feature after the Lth layer. And in particular, we care about this so-called conjugate kernel, which just basically extend the previous kernel that we have looked at in the shadow case, okay? We care about this KCK matrix, this conjugate kernel matrix that tells us the correlation of the features obtained after Lth layer of the network, okay? And the conclusion basically remains the same. So this matrix, this K conjugate kernel, is in a spectral norm sense close to another kernel matrix, K tilde, okay? And this K tilde depends, of course, on the data and also on the activation function, but again, in a very simple way, okay? Only depends on the few parameters. But clearly it's going to be much more complicated than the shadow case because it depends all the activation in previous layers, okay? But we have a way to write them down explicitly. And again, pretty surprisingly, it's independent of all the distributions of the random weights. So all even in previous layers, okay? It's independent of the distributions of the random weights as long as they are normalized to have zero mean and univariance, okay? So here is an informal result because I didn't list out how we characterize these activation functions, but they're going to look like this, okay? So we have a pretty long equation. We know exactly what this conjugate kernel matrix look like, how it depends on the data via a few parameters and how these parameters depends on all the activation function in previous layers, okay? We have a iterative equation that allows us to characterize how this matrix depending on all the design of neural network, but it's pretty, ugly. Great. So since we have this, we are, more or less happy because we can do based on this theoretical result, do neural network compression, right? We can design a new neural network that share the same conjugate kernel as any given neural net, but with sparse and quantized weights and sparse and quantized activation functions using our results. Okay, but we're still not very satisfied because all these results are constrained to the case where we assume the random weights, the weight matrices to be random, okay, which basically tells us this only holds at the initialization of neural network, okay? So we're not happy. We want to do something even that holds for neural network after training. And the good news is there are already existing literature that's introduced a very powerful and convenient tool called neural tangent kernel, okay? So this is a theory that allows us to making the connection of how neural nets convergence and how they generalize and making the connections between neural network after training to its random initialization, okay? So having seen this, we're really happy because we can just borrow this neural tangent, this NTK2 and apply to our idea, okay? So a very quick review of this NTK stuff, this NTK theory. So basically it tells us that under two conditions, okay? First, the neural network must be sufficiently wide, okay? They must be super wide. To be more precise, either you have the width, the number of neurons of the neural network tends to infinity, or it should be at least polynomial large with respect to the data sample, okay? In any sense, it's pretty large. And if under this assumption, and the neural network is trained with gradient descent with sufficiently small size, okay? Because basically you train this with very small step size, then this paper and a few following up papers have shown that, in fact, they introduce called a neural tangent kernel. So this NTK will going to be determined only at random initialization and remain unchanged during training. Okay, so they introduce an object and it's called the NTK, and it's fixed at random initialization. Okay. And as long as you know what's happening at random initialization, you know everything. You know it's not going to change during training, and you have something that you know after training. Okay. So the idea is pretty straightforward. So what we will do is just to extend what we have done for the conjugate kernel, okay, and extend to the NTK. So we have done this, and the conclusion basically remains the same, okay? So we still can have a super long equation that tells us that the NTK of a given fully connected neural nets, okay, what's its behavior, and it's independent of the distribution of the random weights, and it depends on the activations, but only a few scalar parameters. And we know explicitly the equation look like, I'm not showing them here, but they look pretty similar to the conclusion of conjugate kernel in my previous page. Okay, and we're happy we can use this theory for NTK compression, and it's going to hold true even after training. Okay, and here is a figure that we do a numerical evaluation of our proposed methods. Again, it's on real world data. So on top is the meanest handwritten digits classification, and on bottom is CFAR10. Okay. So here the x-axis is again the memory, and the y-axis is the accuracy. So we are looking for the left up corner. So here is always a good performance, less memory and good performance. Okay. And we compare the proposed methods, so all those in blue, and also this in brown. So are our proposed method, and to some very popularly used methods based on, for example, naive quantization or magnitude pruning. Okay, and we show that our proposed method worked pretty well on real world data on deep neural network. Okay. And yeah, so that's the second point I would like to mention, and I'll try to finish by mentioning a few words on our third results on characterize the learning dynamic of deep neural nets. Okay, so NTK, so we have a very detailed study of the neural tangent kernel, and this NTK also allows us to derive in an explicit manner the learning dynamics, so how the loss function change over time of a given neural net, and things we have in our second paper. Okay, so we already have an expression of the NTK, so we think about we can apply this to characterize the learning dynamic of neural nets. And this is first discussing this result. So basically we can write the learning dynamics, how the MSE, the training MSE is an explicit function of the neural tangent kernel, and of course other CK kernel and the label, etc. Okay, and then we just plug in our expression for NTK and CK. Okay, and we get this expression. Okay, this is pretty ugly, but the message is there's no mystery. So everything we have are deterministic. Okay, we assume that the data are Gaussian, and depending on the mean of the input data and the dimension of the input data, and of course all these alpha and beta parameters that depends on the design of the neural net, we can have a deterministic description of the learning dynamic of a simple neural network, as long as the input data are Gaussian mixture. And we have a few numerical results to validate our results. Okay, so we plot this for different ways. We play with the expression and change the meaning of the data, and also activation function. So this is pretty funny, in fact. So in this subfigure A, we compare the learning dynamic from our expression. So all this overlapped curves, and also to the extra learning dynamic using cosine activation function. So this is in this blue curve. Okay, we see there is a pretty large gap. This is essentially the limitation of NTK theory. So we really have to have a neural network that's extremely wide, which is not super useful in practice, so that the NTK predictions can match what happens for this super wide neural network in practice. Okay, but what is pretty interesting that our theory predicts that if we use a cosine similarity and center it so that it has zero mean with respect to Gaussian distribution, then it's not going to work well. It's not going to work well in the sense that the training dynamic is a straight line. It's independent of time. It's always a constant. And we observe this in practice, okay? So the red curve here, this vertical line here is the actual learning dynamic when we use a shifted version of cosine activation function, and we say it's never going to reduce a training dynamic. And we have a theory that allows us to predict this in advance. Great. So I'm almost done, and try to do a quick conclusion and with a few takeaway messages. So with random matrix theory and our toolbox, we have a theoretical analysis of shallow neural network with random widths, and this also extends to fully deep neural network with non-random widths with the help of the NTK theory. And this allows us to propose an NTK compression method with rather strong theoretical guarantees. And these two results are describing the following two papers. And I also mentioned at the very end the learning dynamic results, which are not yet published. Okay. And on my last slide is a Euro advertisement for random matrix from machine learning. So with random matrix, we understand the change of intuition. We have a better understanding of existing methods, whether they work or not, and we know how to improve or fix this method. And with my PhD supervisor, we have this book on random matrix for machine learning. It's published already last year. And we have a pre-production version on my personal website, and all the codes in MATLAB or Python available to reproduce all the figures in the book. So feel free, if you're having any questions or comments on this book and other steps, feel free to send me an email. So that's everything on my slide, and thank you for your time and your attention.
Thank you very much. Very interesting presentation with a lot of interesting results to be applied in particular in deep neural networks, I think. First, let me ask if there are questions in the audience before.
Yes, I may have.
Yes, for sure.
Thank you very much for the very interesting presentation, because I know that you're working on random matrix, but I was always very curious about your work and what exactly is random matrix and how to use that in neural network compression. So I see that there are a lot of mathematical work. I don't know much about the details, but you mentioned that, okay, I would like to have some takeaway message. So,
sure.
So for the neural network compression, so with your theoretical results, it means that we can always find a compressed neural network with randomly distributed Gaussian distributed wave,
yes.
but the so without bias and with a fixed with the calculated activation function, where this activation functions are calculated in some rules, and when you calculate the activation function, you mentioned D0, D1, D2, and I was just wondering how to, so which informations are needed for these three parameters. For example, the information from this information from the data or from the because there are some
good point. Yeah.
symbols.
Yeah, good point. Good point. I'll try to explain this. So here the idea is the following. Okay. So basically, for a given neural network, you would like to apply a given neural network on some problem, on some data for classification, for example. Okay. And the proposed method here we try to we try to, based on the problem, so basic on the data you have, and also the given neural network. Based on this two, we will try to propose a new neural network, but that can be computed more efficiently. And more efficiently in the sense that it has sparse and quantized weights. So it contains a lot of zeros in its weights, and the non-zero weights can be compressed, it can be stored using 2 or 3 bits, for example. And also activation functions. So the activation functions is not ReLU, it's it's a binarized version or ternarized version of ReLU. So it can be stored more efficiently. And what we're try to do this in practice, try to implement this method in practice, we need to use the information from both the given neural net and also data. So basically, for the given neural network, at least in this simple model, for example, here, we will need to use all the activation function. We will need to use the activation function of the given neural networks. This is denoted sigma. And we also need to use this parameter tau, which comes from the data. Okay, so basically for given data and for a given neural net, I first compute this tau from data, and then I compute this activation functions using the activation functions from the neural net to compute the D0, D1, and D2 by evaluating all these expectations. So these are scalar computations and not very super computational difficult. And as long as I have these 3 parameters, for example, they can take any values, 0, 0, 1, or 1/2 or whatever, okay? I have 3 values for this problem and for the given neural net. What I will try to do is to design a new neural network and share the same parameters. So basically, I solve a nonlinear equation. I solve a nonlinear equation in the sense that for given value of D0, D1, D2, I try to solve the behavior, the nonlinear activation sigma that tells us what the new neural network will look like. So how its activation function should be designed. So in the paper, we propose a family of sparse and quantized neural network that are parameterized by only a few scalars. And with that, we can solve a nonlinear, in fact, a three equation with 3 variables, and we get these parameters to design the sparse and quantized activation function for new neural network. And I'm not sure if I explained this clearly.
Yes, thank you.
Okay.
So before I misunderstood because I thought you were trying to train a network from scratch, but it seems that you are trying to compress a neural network which is already well trained. For example, like the very famous networks like VGG or something like that. I don't know much about the names.
Yeah.
Is that true?
Yeah.
Okay.
No. So the yes or no, because I have 2 papers. So the first one is really applied on trained neural nets. So here in this paper, we really, the weights are random. Okay, the rates are random.
Okay.
And in the second case, so where we move on to deep neural nets, yes, we keep, so what we will do is we keep a part of the neural network unchanged. So it's weight GG or whatever, okay? So it's trained, and we propose an NTK based method that allows us to basically compress the network, but even after training, it still have a similar behavior. So we have a way to characterize, even though the theory relies only on random distribution, on random initialization, okay, it still holds even the network after training. So the performance is guaranteed to be pretty well, even after training. And this only holds for the second case. not for the first.
I see. And
Yeah.
you mentioned in this case, you mentioned that there are two conditions. One is that the network should be really wide and
yes, exactly.
And the learning rate should be
pretty small. Yes.
Pretty small. So
yeah.
So even though the network is compressed, then with these two constraints, will the training be slow? Because in what I know is with a very huge network and very small learning rate, learning step, the learning should be very slow.
Yeah. Totally agree. Agree. So that I totally agree. So that's another issue with the NTK theory. So I totally agree that the training may be slowed down since the network is super wide and contain a lot of parameters, and we use pretty small learning rates. And I mentioned this two condition is mainly from a theoretical purpose, because the NTK theory only holds, so formally the theoretically only holds under these two conditions. So that's why most our theoretical results and numerical implementations consider this case. But I agree that in fact, these are not very practical, in the sense that we may want to accelerate the training and even do some even stronger compression, for example.
Okay, thank you. That's all my question. Thank you very much.
Okay, thank you. I had also the same questions. How to compute D0, D1, D2?
Yeah.
Mainly two questions is, when the network is trained, you have parameters, and you want just to compress the parameters without losing any performance during the using of the network. And the second step is that you have a network. You have to want to train again either all the parameters or some part of the parameters, like in transfer learning. And then in that case, also it seems that the performances still stays. Is it true?
So the first for the compression, so I'm not so I know a little bit about transfer learning, but this is not really covered with this talk. But for the compression, at least, so I know that there are many ways to perform modal compression. So for example, what we can do, so what's actually in this numerical results, what we have done is to find a slightly different neural net, because in a sense, what we have done is to change the activation function of the original WGG. So basically we change the neural network and have a theory that makes the carefully changed neural network still perform pretty well with sparse and quantized activation. But there are many other ways to do this. For example, you can have a matrix that it's totally unchanged. Okay, so network is, the structure of the network is totally unchanged, and only compress the weights, for example. Yes, the parameters, for example. And there are pretty few ways to do this. You can train the network and then compress, for example, setting a lot of to zero. This is called magnitude pruning. So a lot of people do this, and then slightly retrain the network, but letting those zero remain untouched. So that's your parameters are still pretty sparse. You have the number of parameters is still pretty small, but you need to retrain those non-zero entries so that to make the network perform pretty good. Okay, so and there are many other ways to do this. For example, they have the training and quantized way. For example, you do one-step training and you do one-step pruning or quantization. So that also works pretty well in practice, but at the cost of taking pretty longer time to train, for example. In this paper, basically, we changed neural network to make this short, in fact.
Yeah. Okay. You change both the structure and the activation.
Yes, exactly. Yes.
Okay.
Yes.
You mentioned that the problem, the optimization problem is a nonlinear optimization. Because you mentioned that there is an nonlinear optimization to do.
Yes.
Before obtaining the compressed network.
Yes.
Can we have any convergence properties of this optimization?
We didn't study this.
What is
it's
the
very,
degree of the nonlinearity, and do we have any measure of the convergence of the algorithms?
So I try to make this explicit. So basically, this nonlinear system of equations or nonlinear optimizations is to solve all the design of these parameters and the design of our activation functions. So a very good point, but for the moment, we haven't done any proof of convergence or proof of regions of convergence to these results. The only thing I can say is according to our numerical results, is that it seems that not all the initializations and settings leads to a stable convergence. So I'm pretty sure that it's worth from an optimization perspective to study the behavior of this nonlinear system of equations and study its region of our initializations of convergence. But for the moment, we didn't say anything about this.
Okay. One last, you mentioned that the whole theory is based on a fully connected network. Do you think that it is going to work also with convolutional neural network, or how?
The same thing. Go ahead, please.
No, just to know if this condition of fully connected and convolutional neural network, which are not fully connected, and are very usual to use. Do you think that the results may change too much if we want to apply it to a convolutional neural network?
We need to make some changes, but I don't think it's technically impossible. So we need to. So the same theory is not going to work, but we can develop slightly by slightly updating a theory to making it work for convolutional neural nets. Basically, by considering a structure in the weight matrices, because for convolutional neural nets, the weight matrices are topless or are block circulant. So we need to take this into account in the theory.
Okay. Yeah. Okay, and the final question that I had.
Please go ahead.
Sorry, was that which one was that? Yeah, it was about the link between NTK and obtaining the expressions for the kernel. It is very interesting because many algorithms, many training algorithms, and also many using during the using prediction step of the neural network, many algorithms are based on NTK and kernel computation. So this point will be very interesting if you have some more connection, how we can obtain, for example, the expression of the kernel for a given neural network.
When you're saying kernels, expressions about kernels, when you're specifically talking about NTK or other type of kernels?
Specifically from NTK, yes.
Okay. So as far as I know, there are a lot of. Sorry, you go ahead, please.
No, you have given some expressions, but I wanted to know if it is easy to compute.
Sure. Yes. Okay. So that can be considered as another advantage of our work, because here I didn't give the details, but in this theorem we have an expression for the CK. but we have a very similar expression for the NTK. So in that sense, this allows us to have a much more easily computationally, feasible alternative for NTK matrix, but only under the assumption of Gaussian data. So because the theorem is derived for Gaussian mixture data. So for realistic data, the theorem formally do not hold. So we do not expect it's going to give an approximation, but we do not know how much this approximation is. Otherwise, I know in the literature that a few papers always trying to find a way to perform the numerical analysis and also different numerical and randomized approach to accelerate the computation of NTK. So I know a few people doing that. But still today, I mean, for large neural network, I think I do agree with the fact that for large and complex neural network, NTK remains pretty an object very hard to evaluate.
Okay. Thank you. Any other questions and remarks from the audience?
Yeah, I have questions.
Yes, go ahead, please.
Yeah, please go.
Okay. So, so thanks for the nice presentation. Could you first go back to the introduction part for the Euclidean distance matrix?
Yeah, sure. I guess here or the slide after.
The matrix, yeah, right after.
Okay, yeah, here, I guess.
Yeah. The image. So here I understand that because I was attending Holman's seminar on spectral clustering. That was a similar idea here.
Yeah, exactly.
So for me, it's like I understand that. So but every time I heard about that, it's counterintuitive. To be honest,
yeah,
it's counterintuitive.
Agree.
So could you, yeah. So I just have maybe a naive question. So if you consider a case where you have two different class of Gaussian distributions,
yes.
and one is like, but how do you say? The mean of the two classes is very far, so they are very far from each other. But the variance of each one. So for instance, for class 1, it's 1 over n. It's proportional to 1 over n. So if n is very big, so the variance is tends to 0 also. And so the same thing for the two. So if their variance is very if the mean of the two classes is very far, but the variance of the both is very small. So is it still the phenomenon holds, or is there some assumptions for your theorem? You say the xi minus xj tends to tau. For everyone.
Okay.
For
Good point. Yes, this holds formally under the setting where we call non-trivial, in the sense that we take this inequality to 0. So agree, and I can tell you the conclusion that if your mean are very separate, so for example, larger than square root of p, the rate, or even p, then you observe your high dimensional problem shrink into a low dimensional one, in the sense that you observe this figure exactly. So the high dimensional figure will look like exactly what you observe in the low dimensional case. So you can treat, you can, what you can in fact do is to just project the high dimensional problem into a low dimensional one and solve the low dimensional one. It's equivalent to a low dimensional problem. Yes.
Okay. I see. So a last question would be, because I know you are expert in random matrix theory, since these are counterintuitive, could you give some like brief description to us? Is there some collection for this phenomenon? Is there some collection between central limit theorem, law of large numbers, all these kind of things? Because random matrix theory, it's I think most of the audience, maybe we are not familiar with random matrix theory, but many of us we are familiar with law of large numbers, central limit theorem. Is there some collection between for this counterintuitive phenomena for this one?
I
understand that
yes.
you give some explanation about the eigenvector. I understand that.
Yeah.
That one is.
So I have, in fact, I have a few slides exactly talking about that. So in fact, random matrix theory is not much more complicated than law of large number and central limit theorem, but I do not have those material ready, so I try to do this with my hand. So the idea is, in fact, the idea is always to establish some sort of convergence. So if you think about this looks like a type of type of so I try to make, try to write something down, but okay, so no, I can't write. So in fact, the law of large number and CLT are different scaling in the sense that, so let us think about this. So if you have random variable with a certain mean, okay, then you sum in a lot of such random variable, you compute its average. This is law of large number. So you converge to the expected value. Okay, you get the expectation, exactly. And this expectation is of order O1. For example, it's a constant that does not scale with the dimension or scale with the number of your observations. Okay, but the CLT is different. CLT basically you subtract the mean and you divide it by square root of p, and you get a Gaussian fluctuation. So basically, the CLT together with the law of large number tell you that if you have a IID independent random vector, okay, for example, X that's leaving RP and have independent entries, then you sum all its entries, okay, all the entries of X, you get in the first order the expectation of the entries of X, okay. So that's given by law of large number. And in the second order, and I mentioned this is second order because it's of order 1 over square root of p, if we sum p terms. And the second order tells you that we do not know it's going to be deterministic or not, because in the first order, it's a deterministic quantity, right? It's mean. In the second, we don't know, it's no longer going to be deterministic. It's only a random fluctuations. And we know it's going to be Gaussian, okay? And here, in fact, we have the same thing. We have the same thing because if we compute this quantity, so it's a vector and a vector norm to the square. We can break this into 3 pieces. So the norm of xi plus the norm of xj and minus 2 times the inner product of this, right? And the norm of xi is essentially something like the law of large number. So it's going to converge to the expectation of it. And the same holds for the norm of xj. So in this sense, we do not say and under the above citing, we only say the expectation of this xi transpose xi times the expectation of xj transpose xj. And these are higher orders because they are characterized by the law of large numbers. And their inner product is exactly the CLT because the xi transpose xj, since xi is independent of xj, they have independent entries. And when we're summing up them up, they give out the xi transpose xj, give us a CLT order. So in fact, exactly the first order is given by the norm, and this tau exactly follows from the expectation. And the cross terms that in fact contain all the lower order informations of the covariance and means, etc., are buried in the second order where we see the CLT. So if we look at the entry-wise, okay, entry-wise, we see this tau is the O1 term that do not scale with P. And we have some smaller order that contains the random fluctuation and also the smaller order informations, okay? So this is exactly due to law of large number and CLT. And if we go beyond this entry-wise calculations, we look at the entries. In fact, we can write all the entries we have done LLN and CLT. We can do the same for all the entries of E, and then putting everything in a matrix form. Okay, I do not have that slide with me, but if we do that, in fact, we'll say this tau going to be repeated everywhere. So it's the tau times 1, 1, 1, 1 transpose. So it's a matrix full of 1 and plus smaller order terms. And there we say random fluctuations and low rank terms that are just in correspondence with CLT and LLN. And this, after doing that expansion, we will exactly observe why we see If you use the second eigenvector corresponds to the second largest eigenvalue, we'll get the classification of the classes. And if you're interested, I can send you a few documents on it. It's very interesting, in fact.
That would be great. That would be great
Yeah.
if you can share the slides later. Okay.
Yeah.
Maybe the second question about the single layer theorem.
Yeah.
So for the K tilde.
Yes. Here, for example, I guess.
Yeah. Here. No, last one.
Next one.
I'm curious about the last one. It's the same. It's the same. Okay. It's the same.
Yeah, it's the same.
It's the same. So the distribution of W, because you say as long as the normalized you have zero mean and the unit variance. So from the theory that tells you, you can just choose a W, no matter what is the dimension of capital N. You just need the W has a zero mean and unit variance, so they can approximate the real kernel matrix.
A good point. Okay.
So you don't talk about the N. I'm curious.
Capital N. You're saying.
Yeah. Capital N.
Okay.
So because the W
here
here
we do not have capital N. Here we do not have capital N. So there are two things. First, we start with the empirical correlation, the sigma transpose sigma, which depends on W. And then we integrate this out. We take the expectation with respect to the distribution of W. In fact, this is the thing we get as the capital N tends to infinity. So we no longer have this dimension capital N.
Yes.
So
exactly. Empirical by the statistical.
Go ahead. Sorry, I didn't get the question.
It is. Go ahead.
Okay.
I follow you.
Okay. So then here we only have the dimension small n and small p, and the distribution on is in fact on this W vector, if you like, which is a vector in dimension p. And I'm saying that it's independent of the distribution of big W. This can be misleading. It should be of the small w here, because I assume the whole W matrix has independent entries and in fact rows that are distributed in a similar way. So we only care about the distribution of the rows. In fact, we even shrinkage, we only care about the entries. So as long as the entries of the W or this W vector, they have zero mean and unit variance, then this result hold.
Because I was thinking about the W is the weighting, because you want to reconstruct, you want to design or construct a new neural network. With the design activation function with D0, D1, D2, and with the weighting matrix also. You have the weighting matrix. So I was wondering about the dimension of the capital N in your matrix, in the design neural network.
Yes.
Because seeing the theorem.
Seeing
the theorem, I thought it was like the W is the weighting matrix of your constructed network, and then the weighting matrix can be randomly chosen just to satisfy, to fulfill the constraint with zero mean and unit variance. Is it?
Yes,
correct?
Exactly.
What I mean.
Yes, that's true. Okay, so here are the two things.
That's true. So
here are two things. Yes, go ahead.
So what I was wondering is, like, you can choose like the dimension of capital N equals to 1. Even equals to 1, maybe it's possible to construct the W such that the normalized to have zero mean and unit variance. But you can also construct the neural network with the capital N tends to infinity. Even compared to small n, it tends to infinity. So you were not talking about the dimension of the choice, and you were not talking about the choice of how to choose the weighting matrix of your reconstructed neural network.
I understand the question. Yes, I understand the question. Yeah, I understand the question.
Like in your figure, you have the naive quantized and some other quantized. So that's what I want to ask. I remember you have some naive quantized and maybe not this one. I saw it
another one
about the compression.
Yes. So I'll try to do this first one. So there are two things. So one thing is the actual design of a neural network that has a finite number of neurons. Okay, you always have a capital N equal to some number. It's never infinity in the actual design of neural network. Okay, so that's one thing.
Okay.
Another thing
yes.
Yeah, another thing is for a given neural network with a fixed number of capital N, you have its underlying kernel by turning the N goes to infinity, by studying the limit of this capital N goes to infinity. You get the objective that I called the kernel matrix here. So when you are at this step, it's no longer this kernel matrix K no longer depends on the number of neurons. So it's characterized the behavior of a neural network, but only for extremely large number of neurons. Okay, and our result here holds only about this kernel matrix K. So basically, it only tells you that the neural network, if you go to the limit of infinity neurons, it's going to give you a kernel matrix, and this kernel matrix will look like another kernel matrix. So it only tells you what's the behavior of extremely wide neural network. And in the simulation results, we do varies the number of features or number of neurons. So starting from 500, which is a large but not extremely large case, and we observe that our proposed approach, which applies to theoretically applies to any neural network, because you can always because it basically does not tell anything about the neural network. It only tells about the kernel matrix. So the kernel matrix can be the same, but if you take the capital N to 1, it's the neural network itself has nothing to do with the kernel matrix. So that's the gap there. And in the simulation, we test a pretty, starting from 5,000, which is a pretty large number, and we see that even it's not infinite, the kernel matrix, the theory based on kernel matrix, still tells us something about actual neural nets. So my quick answer to your question is choose an N that is kind of sufficiently large, in thousands or in hundreds, should be able to apply our theory. So not 1, for example.
Okay, and then how you choose the weighting matrix here? So you randomly choose such that the full field. Okay.
Yeah, exactly. According to equation 3. Yes.
Okay.
So you draw the random. You fix the dimension. You fix the dimension, and you draw randomly the weights according to allow. Yes.
Okay. I see. You use a Bernoulli distribution. Okay. And last question for me is like. Sorry for that. It's still no.
Go ahead. No worries.
Just a small question. It's about the choice of the kernel metric. You're always talking about all the correlation metrics of the feature space, as you said, or you call it the kernel metrics. So every time you want to reconstruct, it's based on this quantity.
Yes.
So as we said, as we maybe in the last question about it, it's like you have your theoretical results, like you have a W tends to something. You just need them to satisfy some constraint. But there are some other statistical moments or some other metrics that can help you to choose how to compress, how to quantize the neural network. Why you just choose only the kernel metrics here?
Because we just start this, and this is the most simple one I can think of.
No, it's not why. I understand. I understand. Even this is super hard. This is super hard. For me, it seems like very hard because the calculation, the derivation. I mean, is there some other thing, maybe some important that is feasible to do or something? Have you think about this kind of question?
Beyond the second moment, for example. Yes. So the intuition is the following. So the second moment basically tells you how things are, the average behavior and the correlation with each other. And if you go beyond that, so what will first happens is we do not have such type of universality. So the universality I'm saying here is we do not really care about the distribution of W, because W, as long as you match the first moment to 0 and second moment as the variance to 1, then it's no longer depends on the distribution. So if you characterize things that beyond the first 2 moments, for example, the correlation here, I'm pretty sure that higher order moments of the weights are going to come into play. So this, in the sense that will allow, so which will tell us how finer things are happening. For example, how should we choose a higher order distribution of the weights, etc. I have think about this. So I haven't done this is first because we just started this, and since correlation makes sense, we do correlation. And second is it seems that the difficulty of duration. So if it's beyond second moments, it's going to kind of go exponentially as the number of moments you're going to consider. And I do not see why we really need a more complicated matrix. So perhaps we are going to do other matrix, for example, some kind of divergence between the distributions of the weights or distributions even of the eigenvalues of the correlations, etc. But I do not see why it is important, or what is the motivations to go much further in the order of moments in the context of neural nets.
Yeah, for me, my question is more about not higher order, because for higher order, even the definition is even to define the problem is quite difficult. You need to use multi-index.
Exactly.
Yes. I forgot that. I forgot that exactly the word. What I mean is that, like, exactly what you mentioned. You like use some other metrics, because now I have the feeling, I have the impression that you have a lot of freedom to design your network.
Yes, exactly.
Maybe you can have a bit more constraint, a bit more guide to design the network. That's what I want to ask. So
yes, exactly.
I totally higher
agree.
order. I know higher order is higher order is. I think higher order is too complicated. It's prohibitive.
Exactly. I agree. I totally agree with your intuition, in fact. And I think what's and then the answer or the question becomes which matrix are we going to study? So the quick thing that's we can try to find out with is how can this matrix connection to the generalization performance of neural network. So we can making that correct connection, then we're pretty sure we can work on a matrix that totally makes sense, and if we can do something that's going to help the generalization of the network. So I guess that's the first step to evaluate, I guess.
Okay, so thanks for all your answers.
The subject is very interesting, and going from the theory to the real applications, there is a lot of questions that arise. And as you mentioned, there are much more free structures and free parameters and free characteristics to freedom of the characteristic to account. But as you answered also is that these are what you presented are those characteristics or those functionals that can be computed and can be characterized in Okay, thank you very much both for the questions and the answers. Is there any other question or remarks from the audience? Okay, if not, I propose that everybody shows himself if they can, if you can, and we are going to upload our speaker, and we hope that in the future we can have much more connections, and we are interested to use deep learning in for inverse problems. And I think that there are much work also to do for those, not only for the classification and regression, but also for some other inverse problems. And nowadays there are many physics informed deep learning methods who are developing. So we will have a lot of things to discuss together in the future. Okay, thank you very much again, and let's clap or
thank you.
Thank you.
Thank you very much.
Thank you for your time.
Thank you very much.
Thank you, and we hope that in the future we can continue to have discussions together.
Sure, of course. Thank you for your time. Bye-bye.
Bye.
Bye-bye.
Thank you. Bye bye.
Bye-bye.
Bye.
Bye bye.
Bye.